give us a talk. He's a Chadev veteran. But before we jump into his, I believe, Dante, you had an announcement you wanted to make? Is that right? Come on up here. Come on up here. Round of applause for Dante.
Spotlight. All right, so everyone, I am putting on together an event for next week, next Friday, June 15th from 6 to 7:30, and it's for some new up-and-coming developers, and it's pretty much a graduation and demo night, so I'm going to give them that platform to be able to showcase the work they've done over the last few months, as well as have a nice award ceremony. There will be food and drinks, and there will be an awesome little surprise that I have in store for everyone who attends. So, and it's free. You can find the event out on Eventbrite, and the title of the event is Graduation and Demo Night. So if you all are interested and you have the free time, please stop by next Friday around on this floor, actually, in this room, in this space, from 6 to 7:30. So that's all I had to say, everyone. Thank you.
All right. Anybody else want to say a word? No? Okay. Without further ado, you guys give a warm round of applause for QP.
All right, hello, hello. Audio okay? Okay. All right, hey everyone. I'm here to talk to you about selling digital goods for Ethereum. So I made a game called Quantum Pilot. I put it out on Steam, which is the largest digital store for computer games, and also on Itch, which is sort of the independent alternative. But I wanted to sell it for cryptocurrency for just to see if I could do it, and also kind of as a resume piece, like, hey, this is possible. So I'll just show you a quick demo for the game. So I'm controlling the ship at the bottom there, and each enemy up top is copying what I do. So you have to end up fighting your past lives, basically, to advance. So yeah, this game is really fun. But if you put it on Steam, they take a cut. You put it on Itch. There's they can choose how much you give to Itch or not. It's not as like a great direct to consumer. It's pretty good though. So what I wanted to do is build a store that lets a user spend Ethereum, which is a cryptocurrency, for it. So you might have heard of Bitcoin. It's the most popular cryptocurrency right now. The main value of it is that you can send any amount of value anywhere in the world at any time. And Ethereum has all of those features, but it also lets you use smart contracts, which lets you program business logic around your financial transactions. So I made a website, and the trailer that is finishing up here, that's shows on the website. And so you can see this is the, oh, hello, Mike. So you can see the user comes to the website, they can watch the trailer, and they can see some information about purchasing it. So the most common wallet for Ethereum, and a wallet is the program that a user uses to handle their funds and send and receive funds, is called MetaMask. It's a browser extension that plugs into Firefox, Chrome, or their own browser. So in this case, it's kind of hard to, am my video okay? Okay. Try this again. I didn't bump it, Brett. So in the top right, there's a little Fox icon that shows that MetaMask is installed in this browser. And what MetaMask does is it injects the web3.js library into the web page. Web3.js is a JavaScript library for interacting with the Ethereum network. So in this case, I'm detecting that Web3 is on the page. The user can watch a trailer, and on that Get Steam Key button, they press that, and they'll be prompted to buy a key. So what actually happens is you have your web page code, and you can look for Web3 and then make calls to Web3 to interact with the smart contract. So the smart contract is the code that I deployed on the Ethereum network to manage transactions. So in this case, the user hits buy, and in the top right, little pop-up says, hey, you've got a new transaction to do, pops up, UI shows up, and the user has to confirm. So you can't force a user to spend money or do anything. Always the UI pops up saying, like, hey, is this what you want to do? And they can cancel if they want. So it shows the price, how much Ethereum they're sending, and there's also the gas price, which is effectively a transaction fee. So I have a default set there. If you put it at the MetaMask default, it can take 20 or 30 minutes for a transaction to go through. And that's because the way Ethereum and most of these cryptocurrencies work is because there's no central authority saying this is what happened. Everyone's broadcasting transactions and then verifying transactions. So the user sends a transaction, and next, that other pop-up that shows up is the signature prompt. So I've got the user, they made a transaction, but now I've got my server with the download keys, and I want to say, okay, how do I know that this connection to my server is the person who just made the transaction? So by signing a message, they're cryptographically signing a message which says play Quantum Pilot, and then I can decode that on my server, and that gives me their address. And the address is a unique identifier in Ethereum. And the user can leave the web page at this point, come back, as long as they can sign in. You can see after about 30 seconds, a Steam key shows up, and they can click that, and it opens up in Steam where they can install the game. Okay, so this is sort of just an overview. So I've got this business process at the bottom. I have digital goods. I want to sell that for Ethereum. So I program a smart contract. That smart contract gets compiled down into code that runs on the Ethereum virtual machine, also known as the Ethereum network. And then the users over on the right, they're going to be sending transactions to the miners, or posting transactions to the network, and the miners are the users that are processing transactions. So every transaction in Ethereum is cryptographically signed. So the users are signing messages saying like, okay, this is who I am, and I'm sending this amount of Ethereum to this function or this address. And the miners are verifying each other's work. So if you try to cheat the system and say, oh, this user sent me 1,000 Ethereum, then you're not going to have the signature for that user, so everyone's going to reject your transaction. So it's as secure as we know cryptography to be right now. This is what it looks like between the user and my web server. My web server in the top right is going to be serving up the website, and it's also connecting to the smart contract. The user's web wallet, in this case MetaMask. Again, MetaMask is the most popular wallet. You can do others. I mean, you can do this stuff with command line utilities if you want. MetaMask is just the most common one, and it's really easy to use. And it really took off in popularity last year. There's an Ethereum game that got a lot of popularity, and so a lot of people installed MetaMask from that. So the user's web wallet will read the website, get instructions on connecting to the smart contract. This is also the same one as my server is, and then send the transaction to the smart contract where the record of their purchase will be stored. So what is a smart contract? So this is the entire smart contract. The language is Solidity. Solidity is like JavaScript, but it's not JavaScript. So there are no null pointers, for example, at least not until a few weeks ago in a recent version. And you can't really do fractions or like floating points very well. So yeah, it's got some other interesting things. So there at the top, pragma solidity 0.4.19. This is saying this code needs to be compiled with at least this version of Solidity for versioning. And next up is a contract definition, a key store. So I've got download keys. I just call it key store. So contracts are first-class citizens in Solidity. That's like the main unit of code in Solidity. And a contract is sort of like it's sort of like an object in other languages, so they can actually inherit from parents, and inherit behavior, inherit member variables. They have member variables, and they have functions on them as well. And you can also do the equivalent of a static function. In this case, it's called a pure function because it doesn't change state on the blockchain. So this key store contract has 3 member variables: owners, owner's num, and developer. And lastly, it declares an event type. So the first one, owners, that is a public variable, and the type is called address, and then the brackets indicates an array of address. So an address is a unique identifier for a user on the Ethereum network. So this is like basically a list of account IDs. And it's publicly accessible, so it can be called from outside the blockchain. And next up is owner's num, which is an integer. It's also public, and this is just to track how many owners there are. Now, I understand in more recent versions of Solidity, you can actually get the number of owners, like you can get the length of an array from an array, which sounds like a really simple thing to do in other languages. But from what I was reading in the more recent versions, you still have to make a second call to that owners function. And again, this is because all this data is being stored on this network. There's not like one single database that you're querying saying, hey, tell me this thing, okay, give me this object, I'll call length on it. It's like, hey, network, what's out there, give me information, and I've got to validate it myself. So it's a little janky, but it works. Next up is the developer address. So an address is a special kind of string in Solidity. Like I said, it's the unique user identifier, and it's indicated in code with 0x, no quotes around it like regular string, 0x, and then this 32-bit hex. So this is the developer address a contract can pay Ethereum out to. And lastly, to declare an event, Quantum Pilot key purchased. The parameter is buyer. It's also an address, and it's indexed, meaning it's easier for third parties to view it, and it'll be sorted in easier to read fashion. So events are how you can announce things that are happening in your smart contract to other smart contracts or to a third party without them having to go in and trace back the whole history of all the transactions. So the first function in the smart contract is buy key. It takes no parameters to it. It has two modifiers, the public and payable. Public means it's publicly accessible, can be called from outside the smart contract, in this case, the website. And payable means you can send Ethereum value to this function. So if you try to send Ethereum value to a function that is not marked as payable, the transaction will be rejected and reverted, and the state won't be changed, and you won't send your Ethereum. And it'll return a bool success at the end. So the first line of this function require message.value is above or equal to some amount. So message is a variable that's always accessible inside your functions, and value is how much Ethereum value is sent in with the transaction to this function. Now it looks like a lot of Ethereum, but that's actually denoted in way. So this is etherconverter.online. Great tool, it'll update in real time if you update any of the text fields. And way is at the top, so 1 and 18 zeros makes up 1 ether, or 1 Ethereum. So that amount there is actually 1,000th of an Ethereum. But you can't really do like 0.001. An Ethereum that's in Solidity that's not going to compile. So that requires basically an assertion. You've got to be sending at least this amount, or else the transaction will be rejected. Next, I'll take message.sender, which is the address of the user who initiated the transaction, and push them onto the list of owners. So that's the owners.push message.sender. And then I increment the owners none by 1. Then I announce an event, hey, a Quantum Pilot key was purchased. It is from this address. And lastly, I return true. So the returning true is not strictly necessary, but it's good hygiene. So in Solidity, we don't really have like a arrow reference or like good use of pointers like in other languages. So if you want to say call function A, and if that works, call function B, a common way to do that is say if function call A, do B. So if you return true from your function, you can always check, okay, if it returned true, I know it worked. There's an exception, hey, we didn't get true. The other function in the contract is the payout function. It takes no parameters. It's also public. It's not payable, so you can't send value to this function. Also returns success. So in this case, this function requires this dot balance is greater than some amount. And what happens is, in a function like this, that's a payable function, anytime Ethereum value is sent to that function, the Ethereum virtual machine will automatically track that Ethereum value gets added to the contract's balance. So when you deploy a smart contract to the network, it has an address and it can store balance just like a user address can. So that'll get stored in the contract's balance. I can reference it with this.balance. And then I can call a function on the developer address called transfer and transfer the balance to the developer and then return true. So a user purchases a key, that creates an event. I want to be watching on my server for those transactions to record who's purchased a key. And then I can call payout and send the balance from the smart contract to my developer address. And that's the whole thing on smart contract side. Just 22 lines, which I think is pretty cool for how much this is doing. There's still a lot to show and a lot to code on the server and the website side, and I'll get into that in just a minute. First, I want to talk about deploying. So I recommend remix.ethereum.org. You can also go command line. There's a tool called Truffle that is the go-to command line tool for deploying smart contracts to the Ethereum network. I had some issues with Truffle, ended up posting on GitHub. Turns out some other people had similar issues. The devs are working on it. Maybe it works now, but I ended up going with this. So this is a in-browser editor. You can also, in the bottom right there, those are functions and variables on the smart contract. You can call them in your browser, simulating the virtual machine. Super convenient to detect errors and test logic without having to go write a web page to interface with this or doing it all through the command line. And if you have MetaMask installed, you can change the environment in the top right there to injected Web3, and now you can just deploy this smart contract to the network from your Ethereum wallet. And so metamask.io, that's a website to get the extension, shot of the user interface. In the top left of that window on the right, it says Coven testnet. So MetaMask has default support for the main Ethereum network, which is like the real world network, the Coven test network, and the Ropsten test network. And you can also connect to your own private network if you want as well. So very versatile. You can import private keys if you want to import accounts into Ethereum. You can see like you have multiple accounts. It's great. Okay, so artifacts from compiling and deploying. So when you compile your contract, you get the contract ABI, application binary interface. And this is just like describes how your functions work. And that's that JSON string at the top. You'll also get the contract creation code, which is this assembly in the Ethereum virtual machine that'll get turned into bytecode for actually creating your contract and having it live on the network. And you also, once you deploy your contract, you will get an address. So you need the contract ABI and the address of where it exists to reference it from your server or website. So on my server, I want to reference the contract, and I need to sync the blockchain, which is the set of all the transactions on the Ethereum network. And one does not simply sync the blockchain. This is definitely the most painful and annoying part of this whole process, was getting this synced. You can see there's a pretty lengthy response to like, hey, why is this thing not working? And here's a screenshot. It might be kind of hard to see, but yeah, so Go Ethereum, or Geth is the most common. It's like the official tool for syncing the Ethereum network. Over 500,000 results for Go Ethereum not syncing. Yeah, so there's some issues out there. Maybe a little column A, maybe I didn't read all documentation. Maybe documentation could have been better. Turns out you're not supposed to run Geth on a hard disk. It will just never finish. You need a solid state drive. So I ended up going with Parity. I still think both tools are great. Both tools devs have been pretty responsive to me on GitHub and other users, and they're actively developing it. I just went with Parity, it's what ended up working for me. And this is what Parity looks like syncing. There's still some kind of gotchas as you sync, like both tools will tell you like, oh, we have a light mode, but you don't want light mode because either there's no peers on it or it's not as secure. And there's like a way to skip ancient blocks, there's like all the old transactions, but then you're sort of relying on other nodes telling you what the transactions are, and that's not as secure. So the way that cryptocurrencies work is each batch of transactions is cryptographically linked from one to another. So you have this unbroken chain, hence blockchain, that like no one can cheat the system. Okay, so that's a screenshot of Parity syncing. And this is my server. So this is a Node.js server. If you're familiar with JavaScript, hopefully this is easy to read. And yeah, significant things here are me importing the ABI and the key address, kind of in the middle there, with require ABI and require key address. The ABI is that, and the key address are the two artifacts from the smart contract being deployed. And at the bottom, I'm going to use the Web3 library and create a new connection to my local host port 8545, and that's where Parity is running by default. That last line there, I instantiate a contract reference calling new web3.f.contract, passing in the ABI and key address. Just a quick warning here, both Web3 and the MetaMask library, and this here is using the Web3 like 0.2 API. There is a 1.0 API, but MetaMask isn't there, and a lot of code out there isn't using that example. So just if you go looking for some examples and the code doesn't look right, double check the version numbers. That caught me a couple times going through this process. But the MetaMask developers are working on porting it over to the latest API. Okay, so I've got to reference the contract on my server, right? So now I need to get the keys, the download keys, and then monitor transactions. So just going to set up some variables. First is a list of owners. This is going to be reading addresses from the smart contract. These are the users that purchased a key. Next is a map of signatures. Mapping the key is going to be an owner address, and the value will be a list of keys that they purchased. And third is going to be, oh, sorry, that was ownership. Second is SIGs. Second is signatures, mapping a owner address to a string, which will be a cryptographically signed string from the user, proving that they control the address. And third is an ownership map, where the key is the address of the user and the value is the list of download keys. And lastly, I've just got a list of keys, which is the contents of serve. So the server boots up, and I'm going to read keys into memory and then call sync ownership. Read keys into memory. In this case, I'm just reading keys from a file. This is really easy for me to manage and easy to just open a text editor and add more keys if I need to. If this thing gets be a really big file, really popular, or I wanted to add other games, I would do a database like Postgres or something reasonable like that. But for now, I'm just going to read the keys in from a file. So sync ownerships. This is where things get interesting for reading from the smart contract. So the server starts up. It calls this function. Right now, it's got a blank slate of its state. And so C is a reference to my contract. And I'll call c.methods.ownersNum. And if you remember from the earlier when I showed you the code, ownersNum was a variable on the smart contract, a member variable. But you actually access it in Web3 like a function. And so you have to call it with ownersNum in the parens. And then you have to do .call on that. And that gives you a promise. And then from that promise, you can say .then, and you get a function with the return values. So B is an error here. A is the value we want. Now, when working with numbers in Web3, so you've got to use the big number library. And this is because like 1 and 18 zeros, JavaScript doesn't handle that too well. So you have to use the big number library to convert this. It's just a map that represents a number into an actual usable number for you. In this case, so inside that callback, I'm saying, all right, let contract number of owners equal the new big number from the value that it gave. So this is how many owners the contract knows about. And if that exceeds the total, which is how many owners I know about as a server, oh, there's a new owner, so I need to assign next key. Else, set timeout and just try this again in 5 seconds. So total, that's just my shortcut function for owners.length, owners being the list of users who have purchased a key, and assign next key. So if total is greater than keys.length somehow, then hey, I need to notify developer add a keys. If this happens though on the front end, the UI will block the user from making a purchase, and it shows a sold out card. So they can't make a purchase unless they like open up their console. So that's just some guard checking at the top. And now I'm going to get to assigning the key. So I pull a key out of my list of keys from whatever the total is. So the first time someone purchases, there's no owner, so total owners is 0. So I get the JavaScript is 0 index, so I get the first key from the list. And now I will call c.methods.owners. So owners is that list of owners, list of addresses on the smart contract. And it's an array. You have to pass in a parameter to get the index of that. You can't just get a direct reference to the array itself. That's why I do that owners num as the second variable. So in this case, I'm passing in the total owners, like, hey, give me the whatever the next owner is that I don't know about. And then I do .call on that. That gives me a promise. And then I say .then on the promise. And that callback function gives me an owner address. So inside that callback function, I will convert to lowercase for convenience later. Then I'll push that owner address onto my list of owners. Next, I check the ownership map. So if not ownership for that ownership address, that means, hey, my server doesn't have a record of ownership for this user address, so give them an empty list of keys. And then at the bottom, I'm guaranteed to have a list of even if it's empty right now for that owner, so push that key onto the list of keys owned by that owner address for that ownership map. And now I've got a record of the user having the key. Next, I'm going to check my sockets. If I have a WebSocket connection from that user, for that user address, I'm going to check inside that first nested if sigs owner address. That means I have a validated signature for that user. So I can go ahead and call the emit keys function, which will send a message over the WebSocket for that owner address. If you're not familiar with WebSockets, it is it's a really lightweight communication protocol that you can send data bidirectional from client to server, and it has much less overhead than making HTTP requests, and you can basically like track the connections. It's like a stream that you have with a client. So it gives you the sort of same effects having like an authentication token kind of, because you're tracking that connection. So okay, that's the same connection, send me data. And if I don't have a signature for that user, then I say emit key amount, which will tell the client, hey, you need, I've got these keys for you, but I don't have a signature. So the client should attempt to verify their signature, which will be the UI workflow and then uploading that to the server to get verified. Okay, so this is how I'm using socket.io and the APIs. You do it like this, socket.on. You have a key, which is the event name, and then a callback function that gets called when that message comes up the wire. So in this case, the client sends up verify signature, call this function, and all those type checks, I'm just type checking to make sure nothing funny comes up the wire from a malicious client. In the middle, though, I've got this statement. So this is a list around a map specifying type string name ethauth, which is short for Ethereum authentication, and value play quantum pilot. So this is the message I'm expecting the user to sign on their end from their MetaMask so I can decrypt it on my end and say, OK, yeah, that signature, that signed message, that matches the address you said you were. Cool, you are that user. So I'm going to use the sSigUtil library for this. And it returns its, when recovering type signature, recovering the address for a signature, it always gives the address in lowercase. So that's why I converted the lowercase, the user address lowercase earlier. I'm doing that here. Sometimes the MetaMask wallet will give it in a, Ethereum address have this special like checksum where if you look at the uppercase and lowercase right, you can deduce some information about it. But yeah, I need to make sure it's lowercase so it'll work with my library. So, and I just do a quick check. So I set from, that's the message is what the user sent up, lowercase, and message.signature is the signature they sent up. If the signature is too short for whatever reason, hey, that's invalid. Emit socket.emit, hey, there's an error, invalid signature. You have this many keys in that amount param. Now I'm going to create the recover type signature param, which is a map around data, which is the statement of string ethauth play quantum pilot, and the sig, which is the signature that came up the WebSocket connection. OK, now I will do a try and get recovered variable and call sigutil.recover_type_signature, passing in that recover type signature param. If that amount equals the from, which is who the WebSocket connection said the address are, great, successfully recovered. My L there, that's a shortcut for me, console.log in there. So I'm just logging out, hey, we successful user. Save that WebSocket connection to my map of sockets, where from is keyed on the user address. And then I assign SIGs also for that from the user address, saving the valid signature. So I never save an invalid signature. So if a user sends up a bad signature, I don't keep track of that. I just like, that doesn't work, try again. And then underneath the console.log recovered, OK, let exists equals has keys from. This is just a convenience function for me. Like, hey, does this user account have keys? They send me a signature, but let's check if they have any keys. And if they do, if the keys do exist, then I call emit keys for that WebSocket, for that user. That sends them to the client. Otherwise, hey, you send me a signature, but you don't have any keys. So emit an error, no keys at the bottom. And then there's just some error handling that it's pretty much the same thing. If you send a signature up and you do have keys, I send you back amount.length. Otherwise, hey, amount 0. And if some exception got thrown in this process, then I send back invalid signature. So just some housekeeping. Something happened funny on the client, and maybe they switched addresses, and if the web page didn't work right or something, no problem. The server will give them the correct info so the web page can keep going. OK, so this is the web page looks like, and I'm monitoring the Web3 accounts, or web3.f.accounts. And I ended up writing a framework, or really just a quick tool for that, and I'll show you that at the end. This is what the user sees if they've got Web3 installed. I detect it, but it's locked. So I detect Web3's presence, but there's no addresses under the account. So it's like, hey, your account's locked, so you need to unlock it. So the user has to, from their UI, open their UI and enter their password. So you as a developer don't get access to that. I don't get access to that. That's like their browser extension handling that. So once they unlock it, so this is the web page. So top two, that $, that's just some jQuery to do some UI updates on those divs. And I'm going to make a socket connection with io.connect, passing my server URL. And I'll just say the socket to window to be convenient. And this is another example of the WebSocket syntax, socket.on, some key, some function. And you can use socket.emit to send data back up the wire. OK, so the web page is getting loaded. And I'm going to track the user account. So I'm using Ethlawyer. That's the tool I created. And it's got a little bit of code to it, but it's not too bad. At the top, I'm passing in the ABI and the key store address, just like I did on the server, where I had to get reference to the key store and ABI and the address of where the smart contract lives. I've got to do that on the client as well, so I can connect to the same smart contract. So zooming in here, I just do window.ethlawyer equals new ethlawyer, pass in the ABI, pass in the key store address, and pass in a callback saying, hey, call this function when the user account updates. So in this case, I will check if the title, the message that comes back is eth-lawyer-account, then I can see if they have an account. So I call hm data.hasMetaMask and address data.address, do some UI updates in the middle with that $jQuery, and I check, hey, if they don't have MetaMask, show an alert, hey, no Ethereum wallet detected, and then I show a no MetaMask display on the UI saying like, hey, you don't have MetaMask. MetaMask is, it's unlikely someone will get here without us, but they might. Hey, MetaMask is a tool for interacting with Ethereum. Click here to install it. And the rest of the UI stays the same, so you can still watch the trailer, still see reviews, et cetera. Otherwise, you've got MetaMask, but you don't have an address. Address is null. OK, hide the key generator workflow. Show the MetaMask lock screen that is this screen here. OK, and otherwise, last case, you've got Web3, you've got MetaMask, and you have an address. Great. So I hide the no MetaMask, hide the lock, and I show the key generator, this is the regular buy workflow. So I will call window.socket.admit, get key amount, passing in window.ethlawyer last address. So ethlawyer.last address is how the ethlawyer tracks the last address the user has. So the reason I wrote ethlawyer is that if a user goes to your web page and the MetaMask is locked, for example, they'll just see like unable to connect, or maybe there's an error. But if they sign in, they still see the same thing, and they'd have to reload the web page. So ethlawyer just runs on a loop, like checking for updates, like, oh, hey, they have an account now. And it saves that as ethlawyer.last address, the last known address of the user. So I'm using that here. OK, so when the document is ready, I'm going to add a event handler on the generate press action. And this is like when they actually click the button, it's going to do some UI updates. And then I'll call window.ethlawyer.filepaperwork. This is my convenience method for calling a function on a smart contract. So the function name is byKey. That array there, empty array, there's no parameters to the function. But if there were parameters, I could put them in a list. Val is the Ethereum value that's being sent. And the 13.37 is the gas price that the user is paying. So gas price is in G Wei, or 1,000 Wei. And Wei is that 118 zeros, that much Wei makes up 1 Ethereum. So it's very little amount. Putting a gas price like this means the transaction will go through in about 30 seconds to 60 seconds. If I leave it at default, it might take 20 or 30 minutes. So that gives me a promise. And I can say promise.then with the result. Like, OK, I just know that it worked. I'm going to call getVerifiedSig to get the verified signature from the user. Otherwise, there was some error. This might happen if the user presses buy and then clicks cancel, or presses buy but they don't have enough Ethereum in their balance. So show an alert, hey, there's an error transaction, please validate minimum balance. Show some UI updates, reset to the start of the buy workflow. And this is just a glimpse at the ethlawyer file paperwork way, lets you pass in the function name of a function on the smart contract, parameters, Wei is the value in Wei, gas price. So if you don't want to use this, you would have to basically write your own code that handles this. Now, you don't have to be generic like I'm doing. You can write it just in line as however you want. But if you're going to be making multiple function calls at different spots, I think it probably makes sense to use this tool or use your own so that you're not having to repeat your code, as well as for detecting the user account being logged in. OK, so the user will get a confirm transaction prompt. And they can just see, like, OK, this is the transaction. This looks fine. They can change the gas price if they want. And they click submit, and that sends it up. OK, so once the transaction is on the Ethereum network, I'll show a loading indicator for the user. And on my server, I'm updating every 5 seconds looking for a new user. As soon as I get one, OK, I got one. Let me send see if I've got a user connected. Oh, hey, that matches. Let me say, hey, give me your signature. So when the server says, hey, I've got this key amount, so that's socket.onKey amount in the client, I'll check, OK, how many keys are there? So if the amount is 0, you've got no keys, and there's also none available, then I show the sold out display. Otherwise, you have no keys, but there are keys available. That's the middle case there. Then, OK, great. No keys, show the regular buy workflow. And lastly is, OK, I've got keys for you, so I need to get your verified signature. And so I've got my log, have keys, get verified sig first, hide the card init, the initial stuff, initial UI, and show the card generating, and then call get verified sig. So get verified sig is going to get the verified signature from the user. So I start off with sig needed equals true, and do some UI updates, and I check local storage. So local storage you can use to store like a one-layer deep dictionary of information. So in this case, if I have a value at local storage keyed at window.ethvalue.lastAddress, that means I've got a signature saved already, so I'm going to try to pull that signature and use that. And so if signatures exist, then I'll say sig needed is false, and I'll call socket.emit verify signature, passing the last address from ethwire, and then passing the signature I read from local storage, and emit that up to the server. And a few slides ago, we looked at the server getting the signature and saying, okay, this signature is valid, and the address matches, okay, I'm giving your download keys. Otherwise, your signature doesn't exist, so sig needed is still true, so I call refresh sig with a callback that's basically going to do what we just did earlier, which is, okay, we got the signature from the user, so load it from local storage, and then emit that up through the WebSocket. Okay, so refresh sig, this is for refreshing the signature, getting it from the user. So zooming in, some UI updates, define an error function, which if there's some error, show an alert to the user, and then emit get key amount back to the server, like, hey, something happened for whatever reason, tell me how many keys I need again. Like, I want to know. Server comes back and says, okay, you have one key, and then that will trigger the client to restart getting the signature again. And if for some reason there is no ethwire.lastAddress, some fluke, hey, I'll just show the error, just a guard check. Okay, so for getting the signature, you'll see that I've got the same kind of statement that I had on the server. The list around the map, type string, name ethauth, value, play quantum pilot. So this is you have to have that format, that type, name, and value for the recover type signature to function. And ethauth is short for Ethereum authentication. So I'll call ethwire.sign, which is my convenience function for saying, like, hey, get the user to sign this message, and then I'm going to use a promise with .then for the callback. And if it comes back and there's no signature, then there's an error. Otherwise, hey, we got a signature, perfect. So I'll save that to local storage, keyed at the user's last address, and then I'll call the callback function with that signature, which will do this here and emit that signature to the server so the server can serve the download keys. And this is what assigning a message looks like for the user. They'll get this pop-up saying, hey, confirm transaction. In this case, they're actually just signing a message. This doesn't cost them anything, but you still have to get their approval, like, yeah, I'm signing this message. And you can see the ethauth play quantum pilot shows up there in the prompt. So they click sign, and that's up to the server, and the server socket emits download keys with some data. I do some UI update, and then call show keys, which will populate the download keys in the list. And that's what I showed you in the demo in the beginning, where that was transacting, then we got the keys from the server, and then that download key popped up. And yeah, this is what the user sees. If it's locked, they unlock it. They click a Steam key, make a purchase, transacting the showing, and then pops up, download keys. And new purchases will load here if they buy another one, and then they're playing Quantum Pilot. So yeah, that is selling digital goods for Ethereum. Hope that's informative. That's a picture of Quantum Pilot co-op. If you grab a friend, 2 controllers, you can play co-op. There's different modes. And yeah, you can check out game on quantumpilot.me, or if you've got Ethereum and want to try this out, quantumpotato.software/quantum-pilot-f. And you can also check out 2 libraries I wrote for this, npm.js.com/quantumpotato.software. The first one is ethauth. Yeah, I should leave this up for a second. Yeah, so the 2 libraries are ethauth for authenticating a user connection with an Ethereum address, and ethwire, which is for monitoring user account changes and interacting with smart contracts. So this is just a screenshot of ethauth. It's just one function, so you just call ethauth and pass in these params. Internal user identifier, that's like your server logic, like your database, like could be an account ID in your Postgres database, or a username, or an email. Identity phrase is the message you're having them sign. In my case, it's play Quantum Pilot, but it could be some token. The Ethereum address, you can see 0x, who they claim to be, what address they're claiming the user is, and the signed data they're passing up. So this just does that same kind of code I did on my server, so you can just authenticate. And if you want to associate a connection with a user in your database with an Ethereum address, you can use this here. You can pass in null for internal identifier if you just want to do WebSockets or something, or you don't need that, but it's there if you want it. So that's ethauth. That's on npm. And I've got an example there too, so it's a React example. You can just run that example and you'll see it work in your browser with MetaMask. And the other one, ethlawyer, also has a working example which will show you the address of a user that's signed in and their account balance. And you can go to open your MetaMask extension and switch the address, and you'll see it update just a second or two later. And you can test this out on the Coven and Robson test networks, and you can search around or email me for questions about that, how to get testnet balances so you can test the stuff out without having to buy Ethereum. And yeah, you can email me, quantumpotato@gmail. If you have questions about this, about other cryptocurrency developments, game development, anything else that comes up. And yeah, that's my talk, and I'm happy to answer your questions.
Cool. Round of applause. Yeah.
Thank you. Thank you.
So we're more or less out of time. Will you be around for a few minutes?
I will be around, yeah. I'll be hanging out for a little
If you
bit.
have questions,
Yeah.
come on up and ask. Otherwise, we'll see everybody next week. Thanks for coming, guys.
All right. Thanks, y'all.